Hello again. This is lecture 6 of a series of lectures I'm giving for my Calc II classes on sequences. In this lecture, I just thought I'd do some more examples of evaluating limits of sequences. What I've got here is 3 sequences listed, and they're a little bit more interesting than the last examples I had talked about. And notice that I've just got the sequence labeled by what the general nth term is. I don't say what n starts with. It's not n equals 1 to infinity or n equals 0 to infinity or whatever. That's because it really doesn't matter what n starts with if you're looking at the limit. So we start at some number and go off to infinity. We're going to be starting at some number for which the sequence elements make sense. So where we're not dividing by 0 or anything. And in this case, if we start with 1 or 0, we should be in good shape. So let's look at these. In all of these, we have a little bit of an issue. In this first one, before, if you recall, we were thinking of, really we were evaluating most of the limits by looking at a function f of x defined on all of the reals. Even though we kind of quit talking about it in terms of a function of the reals, if it made sense, we thought of it as a function of the reals. And, well, what is the problem with this particular situation? Hint, there is a problem here. Give you a moment to see it. Does anybody see it? Okay, the problem is this. -1 to the x makes sense if x is a natural number, but there's a whole bunch of reals between every natural number for which that doesn't make sense, at least when you're restricting yourself to the reals. And as far as our theory is concerned, we haven't even dealt with anything besides that. So at this stage, we're really not going to look at it that way. But we had talked about what happens when you've got alternating pieces. This isn't an alternating series because it's not -1 to the n times the whole thing. But this little piece here is alternating, right? That part here is alternating back and forth, positive and negative. And let's just look at see what that part's going to. Well, what's e to the minus n going to? As n goes to infinity? Right, it's going to 0. And so the whole alternating thing, -1 to the n, it's going to bounce back and forth on either side of 0, but it's going to 0 too. So you can sort of rule out thinking about that thing, and this becomes like the function. This becomes like the function 2n cubed minus n over n cubed. And as n goes to infinity, what's that behavior? Well, this is going to go to, well, it's a cubic over a cubic. It goes to the ratio of the leading coefficients, 2 over 1 or 2. So the idea is this term going to 0 really makes this bottom behave like n cubed, and we can treat it that way. Okay, so now let's go over to this next one. Again, okay, so let me put a big X here. This is not good. Okay, and what about this? Can I think of this as the restriction of a function on the reals? And the answer is no. What is the issue here? Well, the issue is these factorials, right? We don't have a good definition for what x factorial is if x is not a rational number. What is 1/2 factorial? What's pi factorial? We don't know what this is if x is not a rational number. So no, this is not reasonable. So we need another approach for evaluating this. So, well, one thing we could do is we can break it up. One thing nice about factorials is they simplify, especially where they're in ratios. But let's first break this up. This is going to be n over n plus 1 factorial plus n factorial over n plus 1 factorial. Okay, so, well, let's look here. What is n plus 1 factorial? N plus 1 factorial is n plus 1 times the number right less than that, which is n, right? Times the number right less to that, which is n minus 1, times the number directly less than that, the natural number directly next to that, n minus 2, and you continue that way all the way down to 2, then 1, right? But what is this? Yeah, you got it. That's n factorial, right? So this is equal to n plus 1 times n factorial. Or we could think of it also as n plus 1 times n minus 1 factorial, right? So that's going to work with both of these situations. So this is going to be n over n plus 1 times n minus 1 factorial. And this is going to be plus n factorial over n plus 1 times n factorial. And why is that useful? That's useful because here the n's cancel, and here the n factorials cancel, right? And I get this is equal to 1 over n plus 1 times n minus 1 factorial plus 1 over n plus 1. Okay, now why is that useful to us? Well, over here, this is of the form infinity over infinity, right? Which is indeterminate. Both the numerator and denominator are going to infinity. In fact, both of these are of, both this and this are of the form infinity over infinity as well, right? So those are really not easy to work with. We need to simplify them. Those are indeterminate forms. However, both of these now are in what form? Yeah, non-infinite over infinity. That's determinate. Non-infinite over infinity goes to 0. So that tells me this limit is 0. 0 plus 0, which is 0. Okay, so now let's go to this bottom one. This bottom one, oh, it's all right as far as a function of x. I can define 2x cosine x over 1 plus x squared without a problem at all. But the problem is the cosine x just goes back and forth, right? The limit as x goes to infinity of cosine x doesn't exist, so I can't analyze it in that way. And so I'm got to approach this in a different way. Okay, but one thing we do know about cosine of n is that it's bound, right? Cosine of n is always less than or equal to 1 and bigger than or equal to -1. That means Cn, this expression right here, let's do that in a different color. Cn 2n cosine of n over 1 plus n squared is always less than or equal to 2n over 1 plus n squared and bigger than or equal to -2n over 1 plus n squared. And now both of these integrals we can figure out, right? So the first one, well, it's a rational function, degree 1 in the numerator, degree 2 in the denominator, so it goes to what? It goes to 0. The second one, again, it's a rational function, degree 1 in the numerator, degree 2 in the denominator, so again, it goes to 0. And if you recall the squeeze theorem, this thing's stuck between it, and so that's got to go to 0 as well. So this limit is 0. Okay, bye.